Good day, esteemed researchers and curious minds tuning in from around the globe. We're here to delve into the fascinating world of scientific language models with our paper, Galactica, a large language model for science. This research explores how we can revolutionize the way we access scientific knowledge, moving beyond traditional methods and leveraging the power of language models. We'll discuss how Galactica, trained on a diverse range of datasets, can absorb technical knowledge, bridge scientific modalities with natural language, and potentially disrupt the store and retrieve paradigm. Stay tuned for an enlightening journey into the future of scientific knowledge access. The traditional approach to accessing scientific knowledge has been heavily reliant on human effort, leading to a significant bottleneck. This is where language models come into play. They have shown promise in tasks such as citation prediction and knowledge-intensive question answering. However, they still lack the ability to perform tasks in a human-like manner due to architectural limitations. The problem we face is the store and retrieve paradigm of accessing scientific knowledge. It's limited and creates a bottleneck. Existing language models, while promising, still require architectural changes to perform tasks like humans. This is the challenge we aim to address. Our research proposes a novel approach using language models to delve into literature and scientific knowledge. We've developed a method that employs a working memory token approach, which has shown strong performance on mathematical benchmarks. The model is trained on a variety of sources, and its ability to absorb technical knowledge is evaluated. In terms of results, we found that the model is capable of absorbing complex technical knowledge, such as LaTeX equations and chemical reactions. It has also shown promising performance in citation prediction and question answering tasks. Furthermore, we've evaluated the model's potential to bridge the gap between scientific modalities and natural language, and the results are encouraging. This opens up new avenues for the application of language models in scientific research. The traditional method of accessing scientific knowledge has its limitations. It heavily relies on human effort to reason, combine, and organize information. This creates a bottleneck in knowledge throughput, slowing down the pace at which we can process and utilize information. The figure you see here illustrates the concept of model-machine symbiosis, a potential solution to these challenges. This approach aims to disrupt the conventional paradigm, leveraging the power of language models to absorb and process technical knowledge, thereby reducing the human effort required and increasing efficiency. We propose a novel solution to the knowledge access bottleneck: language models. These models aim to disrupt the traditional store and retrieve paradigm, providing a new interface for accessing knowledge. They hold the potential to take on tasks that are currently specialized for humans. However, existing language models face challenges. They don't perform tasks like humans until they undergo an architectural change, and they require support for adaptive computation. To address these challenges, we introduced the working memory token approach. This method has shown strong performance on mathematical benchmarks. It trains the model using a diverse range of sources, including scientific literature and Wikipedia. This approach allows us to leverage the vast amount of knowledge available in these resources, bringing us one step closer to creating a language model that can effectively interface with knowledge. Our research evaluates language models on their ability to absorb technical knowledge, such as LaTeX equations and chemical reactions. We've seen impressive performance in citation prediction and question answering tasks. We've taken a unique approach by using a small subset of available entities for chemical and biological sequences. This helps us avoid bias towards learning natural sequences over natural language. The advantages of language models are numerous. Their context-associative power confers significant advantages over traditional search engines. They can also compose a curated knowledge base, which is particularly useful for knowledge-intensive question-answering tasks. This opens up exciting possibilities for the future of scientific research and knowledge discovery. We propose a novel approach where language models serve as powerful tools for exploring the vast expanse of scientific knowledge. Our method leverages a working memory token approach, which has demonstrated strong performance on mathematical benchmarks. The training process is diverse and comprehensive, drawing from a wide range of sources, including scientific literature and Wikipedia. This approach allows us to absorb and process complex technical knowledge, such as LaTeX equations and chemical reactions, and apply it in a meaningful and practical way. This could potentially revolutionize how we access and utilize scientific knowledge, moving beyond the traditional store and retrieve paradigm and towards a more dynamic and interactive interface. Our research delves into the intricate methodology of training language models to absorb technical knowledge, such as LaTeX equations and chemical reactions. We've also trained these models for citation prediction and knowledge-intensive question-answering tasks, demonstrating their potential in handling complex scientific knowledge. We've utilized a diverse range of datasets in our training process, including scientific literature, Wikipedia, and specialized tokens for chemistry and biology datasets. This diversity aids in the comprehensive understanding of the models. However, we've been cautious to avoid bias in our models. For chemical and biological sequences, we've used only a small subset of entities. This ensures that our models are not overly inclined towards learning natural sequences over natural language. In essence, our research is a step towards creating language models that can effectively learn and reason in a multimodal setting, opening up new possibilities for the application of AI in scientific research. Our research explores the potential of language models to disrupt the traditional store and retrieve paradigm. We leverage the context-associative power of these models, which offers significant advantages over conventional search engines. Our models are designed to compose a curated knowledge base, making them particularly effective for knowledge-intensive question-answering tasks. In terms of experimental design, we evaluated the model's performance based on its ability to absorb technical knowledge. We also assessed its performance on citation prediction and question-answering tasks. Furthermore, we evaluated the model's ability to act as a bridge between scientific modalities and natural language. This evaluation included tasks like automatic protein annotation. In essence, our research is a step towards a future where language models can effectively interface with scientific knowledge, offering a more efficient and intuitive way to access and utilize this information. Our research has yielded some key results that we're excited to share. We've found that language models can perform strongly on tasks such as citation prediction and question answering. They're not just absorbing information, but also technical knowledge, like LaTeX equations and chemical reactions. Moreover, these models can act as a bridge between scientific modalities and natural language, opening up new avenues for knowledge access. The context-associative power of these models gives them an edge over traditional search engines, making them a powerful tool for exploring scientific literature. Additionally, we've seen that these models can compose a curated knowledge base, performing well in knowledge-intensive tasks. This ability to organize and combine information could potentially disrupt the traditional store and retrieve paradigm of accessing scientific knowledge. In essence, our work suggests that language models could become a new interface for humanity to interact with knowledge, taking on tasks that are currently human specialisms. Our research has significant implications. Firstly, it has the potential to disrupt the traditional store and retrieve paradigm for accessing scientific knowledge. Instead of relying solely on human effort for reasoning, combining, and organizing information, language models can play a crucial role. Secondly, these models can serve as a valuable tool for exploring literature and the vast body of scientific knowledge. They can absorb technical knowledge, outperforming retrieval pipelines in tasks like citation prediction. Furthermore, our initial investigations show that language models can facilitate tasks such as automatic protein annotation. They can learn tasks like IUPAC naming through self-supervision and even formulate drug discovery tasks in a natural language prompt, achieving strong results without direct fine-tuning. Lastly, there's a strong potential for language models to take on knowledge tasks that are currently human specialisms. This opens up exciting possibilities for the future as we continue to explore and expand the capabilities of these models. Our research has been focused on disrupting the traditional way of accessing scientific knowledge. We've explored the potential of language models to challenge the store and retrieve paradigm that has been dominant for over half a century. The results have been promising. Language models have shown a surprising ability to absorb technical knowledge, including complex elements like LaTeX equations and chemical reactions. The figure here provides a distributional comparison of citations, further illustrating the potential of language models in this context. This suggests a new, more dynamic interface for humanity to interact with knowledge, one that could significantly alleviate the current knowledge throughput bottleneck. Language models, with their context-associative power, offer significant long-term advantages over traditional search engines. This is particularly evident in citation prediction tasks, where our language model outperforms even the most finely tuned, sparse and dense retrieval pipelines. This indicates a promising future where language models serve as valuable tools for exploring literature and the vast body of scientific knowledge. Moreover, these models show potential to take on tasks that are currently human specialisms. They can compose a curated knowledge base and perform exceptionally well in knowledge-intensive question-answering tasks. This is a significant step towards automating complex cognitive tasks that were once thought to be exclusive to humans. Lastly, our model bridges the gap between scientific modalities and natural language. It shows promise in tasks like automatic protein annotation, demonstrating the potential of language models to learn and understand complex scientific concepts. This opens up exciting possibilities for the future of scientific research and discovery. The need for architectural changes in language models is a key takeaway from our research. These changes are the current bottleneck preventing language models from performing tasks in the same way humans do. We also underscore the importance of high-quality datasets, particularly for tasks like math, which we believe are solvable with language model approaches. Lastly, we are open-sourcing our models to encourage the broader machine learning community to build upon our work and extend it further. This is a collaborative effort, and we look forward to seeing how our work can be developed and improved upon.